And so how do you get confidence when you are designing tall buildings? Can you get confidence by just following Eurocodes or BSc codes or developing a thorough understanding of fundamentals and theories? The most important thing is you must develop a thorough understanding. And because codes will help you, but they will never give you the confidence. Their codes will never give you the confidence to sign and certify a tall building, and especially very special shaped buildings like Altair. So if you want to certify, you must be thorough with your fundamentals, and that's why we always encourage our students to learn the fundamentals and then applications, rather than going directly into applications. And so I'll just take an example, and it's based about direct shear. Any continuous beam is subjected to loading. Uniform loading will have high shear at the supports. And when you are checking for shear, the BSEN or Eurocodes allow you to check it at a distance d away from the face of the support, and then you can provide the same reinforcement up to the support. So if T10 is at 150 sufficient at a distance d away, you provide the same reinforcement within the face of the support and the depth d. But if you look at earthquake behavior, plastic hinges always occur very close to the face of the support. So that means, if you just satisfy the rule given in Eurocode 2, you may not have a very safe building. You must look at Eurocode 7 as well, where you will look at the earthquake behavior, and then take the precautions that are given in that as well. So basically, you have to have certain rules that have been developed by you. For example, if I am designing, I would not like to have a shear force more than 2 newtons per meter, because I know it's better to have a flexural failure than a shear failure. Flexural failure will always give us enough warning, whereas shear failure will give us less warning. So if I want to prevent a shear failure occurring, the ideal is, I know the maximum shear may be about 4.5, but if I keep the shear stress at the maximum shear stress less than 2 newtons per meter square, then the chances of shear failure is very, very remote. Then if I am getting a high shear, then I know the section I have selected is too small. That's why it's happened giving a shear failure. In a reinforced concrete structure, increasing the width of the beam by 50 millimeter or 100 millimeter will not carry a huge penalty. So it's worth increasing the width of the beam by 100 millimeter than having a very high shear stress. So you can have various rules, and the reason is you have to always think which failure you like to have, and then you have to ensure that particular failure occurs in the structure when it is overloaded. And then again, what you do is you will take additional precautions against whatever the failure that you like to have. And generally, I like the beams failing in flexure because it always gives sufficient warning. And always you have to think about the type of earthquakes that can occur. And Sri Lanka will not have earthquakes generally, but earthquakes are most unpredictable events. So if an earthquake ever occurs, it would be in interplate type, because we cannot 100% rule out any earthquake in Sri Lanka. The reason is in 1614, on April 14th, there was a massive earthquake reaching a magnitude of 6 on Richter scale, about 15 kilometers away from the western coast of Sri Lanka. So the epicenter was only 15 kilometers away, and it caused massive damage to Colombo. So because of that reason, we cannot rule out, and also the deep studies undertaken by Dr. Kushan Vijayasundara and his team also have indicated that the western coast of Sri Lanka can face higher chance of earthquake than the eastern coast, although we often hear some tremors in eastern coast. So western coast of Sri Lanka can have a higher chance of earthquake, but again what we have to keep in mind is intraplate type earthquakes, or the earthquakes that occur within a plate, is a very rare event. And even in an area where the plates are moving, earthquakes are not events that will occur every year. They are again, they are not very frequent events. For example, if you look at the Great Californian earthquake, which was of 1906, for the last 100 years or 110 years, we haven't had any major earthquake in that area except 1991 North Bridge earthquake. So everybody in that area or western coast of America now expects an earthquake can occur in a moment. So what you have to do is don't blindly follow the codes. Always develop your own rules, and then you can use codes and do the calculations. And if the answers that you get do not tally with your rules, you can always recheck. But if you do not have your own rules, then there's no way you can check and ensure that your answers are correct. So let's see some guidelines. In buildings, if you are considering the vertical load carrying system, the main vertical load carrying system consists of columns, walls, pile caps, piles, and columns can be massive, but again, we can't increase the size of the columns too much. So because of that reason, we generally tend to use higher strength concretes in columns. And if you look at the Eurocodes, I will use only the cube strengths, because the Eurocodes allow us to use either cylinder strength or cube strength. So I'll talk only in terms of cylinder strength to avoid any confusion. We are allowed to go up to 105 newtons per millimeter squared or megapascal as the maximum strength. Whereas, in most of the constructions, you will find that we are using 25 or 30 megapascal concrete. And then walls can be of any thickness. And as in Altair, if you want, you can use diagrids. And the minimum reinforcement requirement on columns and walls of walls according to Eurocode is 0.2%, VS code is 0.4%, but it's very usual to find that you are getting about 1.5 to 2.5% reinforcement. And when you are using a column of something like 1.2 meter by 1.2 meter, and when you are using some concrete like 100 megapascal, it's very usual to have massive column loads, like something like 80,000, 9,000 kilonewtons, or 80,000 or 90,000 or 90,000 kilonewtons or 9,000 tons. And you can just imagine the weight of a vehicle, a lorry, maybe about the container truck or a cement lorry carrying 600 bags of cement, will have a total weight of only 40 tons. And here we are considering a column carrying a load of something like 80,000, 90,000 kilonewtons. So then if you are using 4 piles, each pile will have to carry about 25,000 kilonewtons. And to have a pile carrying 25,000 kilonewtons, we might have to go for 1.8 or 2 meter diameter. And when you go for such diameters, still, you might have to consider socketing into the rock 4 or 5 meters to ensure that adequate skin friction can be developed. And sometimes to increase the skin friction, you might take very special precautions like, breaking the rock around the file or having a groove or with special tools or some special feature that will allow us to go for higher skin friction like 1000 or 1500 newtons per millimeter squared, whereas if you look at ICTAT specification, for normal conditions, it allows us to go only up to 200 kilonewtons per meter squared, whereas now we are talking about 1000 kilonewtons per meter squared or 1500 kilonewtons per meter squared. That means we had to have very special precautions taken. Then only these very tall buildings can become practically feasible in our conditions. So our conditions are very favorable, but sometimes you have to do supporting great depth. For example, in Altair project, the rock was fractured. So to capture adequate skin friction, the piles were driven 10 meters into the fractured rock. And that gave massive skin friction. And when the piles were tested, even at 1.5 times the actual load, piles did not show any movement. So you can see, very special precautions are needed. And once you have this kind of knowledge, where you look at it in a more objective manner rather than just as a mathematician, it will give you a lot of confidence that, your structures are good and correct. And you have to take adequate precautions when you are having columns, beams, piles, and especially the ground beams and so on.